In today's lecture, we will be talking about algorithms that allow us to validate some signal from sensors. And we will spend 2 lectures on this topic, since it's again a little bit larger topic. And I will give you an overview of those algorithms, how they work, and then I will show you some examples of applications where can you use them, and also some MATLAB codes, and we will run the codes and we'll see how this algorithm works on some simulated signals. So first of all, let me talk about what is it good for. Where can we actually use this kind of algorithms? Well, those algorithms will be useful to detect missing values in data. So for example, let's imagine you measure temperature, let's say in an oven, and due to interference or due to some cable problems or due to some noise, the data that you get from the sensor suddenly disappears. But it will disappear, for example, only for one sample. And you can get either no data at all, or you can get some wrong data, some completely wrong readings, for example, due to interference. Now, if this happens for one sample, it's usually not a problem. But what if it happens for more samples? What if I get missing data for 10 samples or for 100 samples, and then it comes back? So I will need some way how to detect this problem and how to eventually raise some logic signal that will say, attention, there might be something wrong with your data. So we will use those algorithms to detect if there are some missing values. The second purpose of the algorithms that we will discuss might be that we want to insert some missing values. So let's say, again, I measure temperature in an oven. For the last 10 samples, it was 200 centigrades. And now suddenly, I have a reading that's saying it's 500 centigrades. And then the next sample will give me again, it's 200. So it's obvious that this wrong value is not physically possible. You cannot change the temperature within one sample time from 200 to 500 centigrades. So you need to raise an error message, or you need to remove this data from the measurement. And instead of this measured number, you may want to insert some value. So let's say, for example, you will calculate an average from last few samples, and in this case where you have this wrong data, you will insert this average value. This is called also data imputation, and obviously this will work only for a short period of time. So you can use this only for few samples, because you don't have any prediction in long term how will the process behave, what is changing, if you will have changes in temperature, and so on. So this will work only for a short period of time. It will obviously depend on the sampling rate, because for some systems you will need a sampling rate of, for example, 1 minute. You don't need to sample faster. But for some other systems you may want to sample every second or every millisecond. So there is no specific time that you can say that this method will work, but it will be purely related to your sampling time. The third possibility that we want to use this algorithm is that we want to verify that the data that we have is suitable for further processing. So for example, we may want to check the uncertainty of our data online, and based on this uncertainty we may say if the sensor measures correctly, if it has a smaller uncertainty, or if it will have a large uncertainty. We will just discard the data because it will be really problematic to work with this data. So for example, again, let me use the temperature example. We measure a temperature in a room. We know that it should be somewhere around 20 centigrades, and we get an uncertainty of our data of, let's say, plus minus 1 centigrade. Then we may find that this is okay. We will be fine with measuring 20 centigrades plus minus 1. But then something goes with the sensor, or you may have some interference in your signal, and suddenly your uncertainty will increase. So you will still have the 20 centigrades, but now it will be plus minus 10 centigrades, or plus minus 20. And then, based on this uncertainty, you may tell that there's some problem, and that you probably will stop the process, or make some warning, or discard the data completely, because if you measure 20 centigrades with plus minus 20 centigrades uncertainty, then certainly this is wrong. And the last point that I would like to focus on in this topic, in these lectures, is how to use the algorithms to increase reliability and safety of the system. So how to combine, for example, some signals from several sensors of the same variable, and how to say that my system is secure because it measures the same values from all sensors, and that I can rely on this number. So this will be about critical systems where you need some redundancy in your sensors and in your data. I will also talk a little bit about the topic that's called self-validating sensors. And this is nothing else than a sensor that has those algorithms embedded. So we will be able to tell if the sensor measures correctly, or if we will have some trouble in the sensor. So here is such an example. This is some real data taken from a flow sensor. It's taken from this paper, and they have made an algorithm that allows you to tell if the change on the data is actually possible, or if this is an error in the sensor. So let's take a look here. Here, this relatively straight line, well, almost straight line, is the actual flow rate. So we can see that the flow rate is not changing. You have a flow, for example, in a pipe, and it's constant. So for all the samples, we are somewhere near let's say 2.5 kilograms per second. Of course, here we can see some noise, but the point here is that suddenly at this time, 10 seconds, the output of my sensor drifted to some other value, and now the question is this really a change of flow, or is this an error of the sensor? But without any further data, we cannot tell. So just by looking on the signal like this, you cannot distinguish if this was some change in the input of the sensor, or if this is some problem in the sensor. So for example, it might be some interference, or it might be some problem in calculation. Typically those kinds of sensors, they use some microprocessor, so it could be a bug, or it could be some change in the connection between your computer system and the sensor itself. But here, without any further info, we cannot tell what is the cause. So this is a block diagram how the data validation process will typically look like. So on the input, we will have some data from our sensors. So this will be real data that's coming in. It might come in as analog signals, voltage or current. It may come in also as some digital signal. Here, if it's an analog signal, we will need some analog to digital converter so that we digitize the data, because the algorithms that we will be talking about will be digital algorithms. So we will need some sample data. The second input here that you see called soft sensors. This is an input that comes from sensors that are not real, that do not exist in hardware, but those sensors use algorithms to calculate variables that we want to measure as well. So for example, let's say I want to measure, for example, temperature of some gas, and I know what is the pressure and I know what is the volume of my gas. So you know from thermodynamics that there is an equation that relates the volume, the pressure and temperature, those three variables. So if I measure 2, I can calculate the third one. And you can imagine that this is a kind of soft sensor. I don't need a sensor for temperature because I have a mathematical model or some equation that allows me to calculate the variable that I want. So the soft sensor is nothing else than other algorithm or like mathematical model that is taking data from some other sensors, calculates this mathematical model and produces some data. Sometimes in automatic control this might be called, for example, an observer. So you have some online mathematical model and you run this in real time. Regardless of the origin of the data, we need to process the data somehow. So we then typically take this data and we clean it or we remove the noise. So we may use here, for example, some low pass filter or some high pass filter, notch filters, for example. And the purpose of this block is to clean the data of what we do not want in the process. For example, if we measure temperature, then we know that the temperature changes due to heat capacity can be relatively slow, so we can remove all high frequency data. And we will not focus on those algorithms. This is for like a probably different class. I think you already had or you will have maybe some class about filtering, at least some lectures. Then the data that we have on the output of our filter comes into a block that will verify if the data is valid. So in today's and next lecture I will be talking about this part of the block diagram, so about the validity of the data and about the data imputation. If the data is valid, then that's fine. We can forward the data to some further algorithms. We may do let's say image recognition, we may search for some patterns, we may do simple thresholding and so on. So this is then the clean data that is validated and we use it for some process. Now if we find out that the data is not valid, we will first check if the data is complete. It means, for example, we might be missing some samples. For example, if you have digital communication, then typically the data is being transferred with individual bytes or packets. And when there is, for example, some interference that is like quite short, it may destroy only one number or it may destroy only one packet. So then you have the previous data, the historical data, then you're missing one or few samples, and then you have data again, which is correct. And in this case, you may include the historical data by some average, for example. And if your data is not complete, you may you may edit in there. If the data is complete, well, you can either use it in the algorithm or you can discard it. I think that there is some problem here in the well, probably not, because if you don't have valid data and if it's completed, then you don't know how you can add some data, so you really will discard the data. But if you know how to add the data in there, you will use the algorithms that we will talk about, and then you verify again if the data is valid using basically the same algorithms that we had here in this stage. And if the data is now valid, we can forward it to further processing. And if it's not valid, we will discard it, because there is no way we can actually correct this error. So we will move along this block diagram. We will not talk about those blocks, data acquisition and data cleaning, but we did talk about sensor fusion, which was belonging of kind of here in this group, in this sensor input. And now we'll be talking about basically those blocks here to verify the validity of the data and edit if we really require it. I will be talking about 3 groups of algorithms, and some will be fairly simple ones, so I will just mention how they work, and I will not go deeply in mathematics how it's done, because it's really simple. Some will be algorithms that you already have seen in the sensor fusion group, so I will not talk about them either again. But I will only focus on basically 3 new algorithms in those 2 lectures that we will see and we will play with in MATLAB. So the first group is an algorithm that can only detect if you have some wrong data. So it will tell you that there's something wrong with your data, but it will not be able to correct it. So the only thing you can do is to set some logic signal that will say an error in data, and then it's up to you as a programmer of the control system, what will you do with that? Will you discard the data, or will you stop the process, or whatever you require? The second group will be able also to correct the data. So it will in most cases have some internal mathematical model, but here let's use this word in quote marks, and this model will be able to predict what should be the correct number with some probability, and it will allow us to also correct the data. So the second group will be able to detect that there's something wrong, and it will also be able to say, how should I change it? How should I improve the data? But of course, it will be, all the algorithms will be related with the sampling rate, and they will not be unfailable. So it means that it will work only for a short period of time. And the third group that I have called other will be something else. So it will be some other algorithms that may help me in understanding my process and in creating some description of this process, so that I can say, okay, now there's probably something wrong with the process or with my measurements. So let's take a look first on an overview of the detection methods. So those will be the first group, so the methods that are able only to tell me that there's something wrong with my signal. And I have split those methods into simple methods, and then on the next slide we will see some more complicated methods. And those methods you will probably already be familiar with. So the simple test methods might be as simple as you are detecting a 0 or a constant value. So for example, let's say you measure temperature again and you know that you measure temperature in a room, and it should be somewhere around 20 centigrades if everything is okay. But suddenly you get zero values. So that might mean that it's, for example, freezing in the room, which may happen as well, but it's not very likely that we do not heat a room where we live in. So the zero value on my temperature reading might mean that there's something wrong with my sensor or with my signal. So the detection will be very simple. I'm looking for a value that is near my expected value, and if it's outside, if it's, for example, 0, then I say there's some problem. You may also look for a constant value. So for example, let's say you are controlling a heater, and you turn the heater on and you observe or measure what is the temperature of the heater with some temperature sensor. And you know that you have turned it on, so it should heat up. So for example, you have started at, let's say, 20 centigrades, and it will increase the temperature, and you know that the steady temperature will be somewhere, let's say, 80 centigrades, for example. So you turn it on, you wait for some time, and then you check what is your temperature reading. And if after some time the temperature is constant, it means that either it's not heating at all, so you have a problem with the heater, or you have a problem with the temperature sensor, because it may heat up, but the sensor is faulty and you will still get the original temperature, like 20 centigrades. So the way this is typically done is that you turn something on, such as a heater, and after some specified time you will verify if the temperature has changed. So for example, you start at some initial temperature, you say, okay, I'm starting at 20 centigrades, and after 1 or 2 minutes you will check if the temperature is significantly larger than this 20 centigrades. And if not, then you will signal an error saying either the heater is faulty or the sensor is faulty. So this is like a really simple algorithm. I'm sure you would be able to code your own code for that, so I will not focus on this. The second possibility that I would like to discuss is to detection of a minimal or maximum value. So again, let me use my temperature example, and let's say we will measure temperature with a thermistor. So a thermistor is a resistive temperature detector that changes resistance with some temperature, and typically it's connected like this. Here we have our temperature sensor, here we have some fixed resistor, and this will be plus some voltage, so let's say, for example, plus 5 volts, and the output signal is here, and this goes to your microprocessor with an AD converter. So we can see that the voltage that we measure here will be a function of this temperature, and we also know how the steady state characteristic of this thermistor looks like. So here we have the temperature theta, and here will be the resistance of my thermistor, and we know that it's an exponential curve, so it will look something like, well, it should be an exponential curve, so something like this. And now we measure the voltage here. What happens if the sensor will be destroyed, for example, like mechanically, or if for example the wire will be cut? Then what happens is that this wire is disconnected, and on the input of our AD converter we will get the full 5 volts limited by only this resistor, so full 5 volts. And the typical outcome of this is that, let's say you measure temperature in a room, for example, so you know it's somewhere around 20 centigrade. But when this happens, when this sensor is destroyed or disconnected, you will get some reading that's something like minus 150 centigrades. So, okay, I can measure minus 150 centigrades with the thermistor. But in my application, where I measure the temperature in a room, now this is very suspicious. So this is most certainly wrong reading. And I can simply eliminate this problem by detecting the minimal and maximum value. So for example, I expect that my temperature as a function of time, let's put it as theta here, so I should be somewhere around 20 centigrades, like this. And I assume that the temperature in a room will be somewhere in the interval of, let's say, maybe 10 centigrades when I'm not at home in winter, up to, let's say, maybe 30 centigrades when it's really hot in summer. And if I'm inside of this interval, I will say, okay, the sensor reading is correct. But if I'm outside, if I measure, for example, 50, then there might be something wrong with the sensor. If I measure minus 150, then I'm certainly getting a wrong reading from the sensor. So this detection, that's nothing else than an if condition that you have somewhere in your code and saying if it's larger than this, then signal an error. A very similar is the thresholding case. This is basically the same stuff here. You are watching if you are in the correct interval, and you may also watch for this interval for some given number of samples. So for example, let's say here you have your samples like this, that's your measured temperature, and then due to, for example, interference, for one sample you will get it's minus 150, or for one sample you will get it's plus 80, and then it will go back again around 20 centigrades. So in this case there's no reason to signal an error just because of one sample, and you may simply discard this reading, or you may replace this with some historical data. The next option is signal gradient, and this assumes that we already know something about our system. And I will again use the example of a temperature sensor. So let's say I'm controlling a heater that heats a room. I will turn it on, and I know what is the time constant of my heater. So I can calculate how long will it take before I reach some specific temperature. And here is an example. Here I have temperature versus time. This is a transient response, shown as a transient response of a first order system. And here is a step change. And this step change might be the power that I'm delivering to the heater. So I have, at time 0, I have turned the heater on. And I expect that it will heat up. And here I can really see the reading. This is those points here, that's the measured temperature, and I know that it should follow some exponential curve because I know what are the properties of my system. And I can calculate the gradient, in other words, how fast is my signal increasing. And this is this tangent here, shown in green. So at some point I will calculate the gradient, and if it is near what I expect, then my signal is okay. So you usually do not check for a specific value, like a fixed number, but due to noise you always will be checking for some interval. So let's say an interval like this. So if the slope of my gradient of my curve here is in this interval, then it's okay. If it would be, for example, something like this, let's plot another curve in this chart. So for example, I turn the heat, not the green one, I turn the heater on, and then the reading that I get will be something like this, for example. But I know that it should be like that, because I know what is the thermal behavior of my system. So then this is telling me that there's something wrong, either with the heater or with the sensor itself. But in this case, it's probably the heater, because it's heating up, but it's not heating as fast as I expected. So maybe I have a problem with some section of the resistance in the heater. So by checking the signal gradient, I can tell, okay, everything is in the correct interval, so basically in this region, and that's fine. If it's outside, I will signal an error. And the third possibility, and that's what I will focus on today, is that I can observe the probability distribution of my signal. So I can plot the samples in a chart, and I can observe if this chart has a specific shape that I'm expecting, or if it has not this specific shape. And we will see that later. This will be related also to uncertainty, because in both cases we will plot basically very similar looking charts. So those are the simple methods. I'm sure that you will be able to code yourselves those 4 cases, and I will show you only this last one. This will be my very first example in a few minutes. The more complicated detection methods may be based on very complicated algorithms. So they may be based, for example, on some mathematical or physical model. So we will describe the system, for example, with some differential equations. We will make some block diagram, we will simulate it somehow in Simulink, for example, and we will feed our sensor data in this mathematical model, and we'll see what is the result, and we'll compare the calculated values with the measured ones. And based on the difference, we may tell that there's something wrong in our system or not. So I will not focus on this, although the mathematics and the physical reality of the model will always be hidden in our equations somewhere. And there is I think a special subject with Professor Vyhlídal about the mathematical models, and about he's focusing on control, but it's basically the same equations, the same description of the system. Then there are 3 possibilities, and I will neither focus on those of them. You may use a very complicated structures like neural networks, state machines, or you may use data mining. All those algorithms are quite popular today. I believe there is one subject that is talking a little bit about neural networks, and I think you have it in the next semester. Anyway, those methods can also be used to detect, and they can also be used to correct the data. And we'll not be talking about those methods either. I just want to stress out that they exist, and you will be talking about them somewhere else. What we will be talking about are those 3 methods. One method will be called Principal Component Analysis, PCA in short, and I will be talking about this method on the next lecture. Now, we have been already talking about the Kalman filter without knowing that it's also useful to signal detection. So Kalman filter, that was 2 previous lectures. And we'll talk about probability methods a little bit. So we will see how we can use the probability distribution to detect if there is something wrong or not with the system. So PCA will be for next lecture, Kalman filter we've already covered that, and probability methods will be on today's lecture. Then the second group will be the correction methods, and those methods are able to not only say that there's something wrong with my signal, but they also can tell me how can I remove this problem in some short period of time. One example, one very simple example, is you can interpolate your data. So let's say you have some data, and this data looks, for example, like that. You see some variable y as a function of time, and then suddenly you have one sample like this. So you may either discard that, or you may base your reading on the last value. You may say, okay, this is not possible that such a fast event has occurred. So you will base it on the historical data. So for example, you will take those values that you had here, and you will use the last one, or you will base it on some trend that you had in the history. You may also filter the data somehow. So for example, if you have such a peak like this one, you may use a kind of, for example, low pass filter that will filter out the high frequencies that has occurred here. Another option is simply calculate a moving average. So you take few data in the history, like 4, 5, maybe 10 historical data, and you calculate a moving average or a median in some cases. And this works quite well if you need to get rid of this kind of problem, like very fast peaks. So this will be like a simple filter. So I will not be talking about those methods either, because I think interpolation, it's fine, it's very simple. Filtration, moving average, we've been talking about it, and the other kinds of filters are covered in different subjects. Of course, here you can use again more complicated methods such as data mining or neural networks. So you can see that some of those methods, they belong in both groups. So they are able to detect the problem, and they are able also to correct the problem. So for the correction methods, we may use algorithms such as Kalman filter. We've been talking about it. In some other subjects, I'm not sure what's the name of the subject, but I think it's with Professor Freiter. You will be talking about that. Those are, let's say, basically statistical methods. And then just some name that I want to stress out: linear predictive coding. So all those are correction methods that allow you to correct your problem in a short period of time. And obviously there will be many more methods. So here those 3 dots, more methods are possible. This is just a very brief overview of the methods that you may use. What are the other methods? That we will cover only one of them. Those other methods are typically not based on some mathematical description, although that's not entirely true about this, not at all. But they may use something else. So for example, if we want to validate the signal from the sensor, we may perform sensor calibration. So we will schedule a calibration every 3 months, every year, for example. And by calibrating the sensor, we make sure that it measures properly, it's working, and it is within our specified accuracy. So this is not like, let's say, a method that is based on some online estimation. but it's also a method that allows us to validate the sensor from time to time. And here, the first one, we can also measure the time from last maintenance. During this maintenance, we may perform, we can visually inspect the sensor, we can measure the voltage, we can measure the power it takes, and so on. We can calibrate it as well. And we can schedule this maintenance every month, every year, whatever is required. So this is also a method that allows us to verify the proper function of our sensor. And the only method in this group that I will be talking about is I want to calculate the uncertainty of the data from my sensor. So this will be based on some statistics, and I will plot the data and I will calculate something with that. And I will be talking about this method on this lecture in a few minutes. So what are the possible strategies? What may we do with the data that we get? Well, there are basically three strategies that you may use. So you have some raw data that is coming from the sensor, and on the output of your algorithm, you want to have the data that has been verified or corrected, plus you want to have some logic signal that will tell you if the signal is okay or if it is not okay, if there is an error in your data. So the simple strategy is that this is your raw data that's coming in. Then you see here, okay, I have some constant data, this is correct, and then suddenly I have some peak in the data like that, and this is certainly wrong. So what will I do about this peak? I need to process the data somehow, and I need to output what we will call a validated measurement signal, or VMV in short here. So this will be my validated signal. And the simple strategy takes simply exactly the same data. So you just copy the data from the input to your output. But then you say on your logic signal, which is here, that the data is bad. So here we have a logic signal that is saying this data is correct. And then here I have my logic signal, and here I'm saying data is bad. And then I have correct data again, and I have good data on the output. So this is a simple copy from the input to the output. And then it's up to the control system that is connected to this block what he will do with it. So either he will discard it or he will not control based on those data, whatever. So this is like a really super simple strategy. The second possibility is that you detect the problem. You say this is a wrong signal, and since it's a wrong signal, I will not output any data on my output. So here I will miss some portion of my signal, and at the same time I will also signal that there is a bad signal available here. So I will not output anything, and here I will signal there's something wrong. And basically the third possibility is that I will detect my problem here, I will correct it somehow. So for example, here I will just take the last sample that was correct, and I will use it until I have correct data again. And at the same time I will have this signal that signals me that there's something wrong with my data. So we will see basically this strategy C, because you could code very simply this data here, but just signal it, copy directly data and signal somehow that it's wrong. So we'll see how to produce this logic signal, but we will not focus at all on this option where we're simply copying the data. or on this option, because this option is simply discarding the data. So today we'll focus on how we can get this signal, that it's good or wrong. And today and next week we'll see also how we can actually work with this correction. So let me start with the first method, which will be the online probability distribution. So this method can tell me only if there's something wrong with the data. It cannot correct anything, so I will just have a logic output saying there's something wrong or it's fine. On this picture I have data that I have obtained from an accelerometer. So I have measured the acceleration in a single axis. My accelerometer was not calibrated, so that's the reason why it measures around 12.5 Gs, not Gs, meters per second squared. If I would have calibrated that, it should measure 9.81 approximately. But that's not important. The important fact here is that I'm sampling the data, and in this kind of process I can assume that I will get a normal probability distribution, or in other words it's called also Gaussian distribution. And the Gaussian distribution is looking like this. It's like this bell-shaped curve, looks like this. And I have some mean value, and then I see that the values that are on the left and on the right from my mean value are less probable. So if you plot this probability distribution, you'll find something like this. Let's say you know that you measure the acceleration in the z-axis. For example, you are on some drone, for example, and that you know that you are on Earth, so this value of acceleration should be somewhere the expected value. So if it's calibrated and if you are on Earth, then you will have something like 9.8 approximately. Then you will have some noise, so you will not get a single value, but you will get some probability distribution. And if you have enough samples, this will be a Gaussian distribution. So it will be looking like this, and here you can measure what is the width of your variance. So it's typically measured as 3 sigma. So you have a mean value, and here you can get what is the width of 3 sigma. In other words, what is the variance of my signal? How does it vary from the mean value? And let's say you have a good sensor. It measures properly, there's no problem at all. So what you will get is a fairly narrow curve like that, where you will have some mean value and then some small value of variance here. So we know that like this is a fine sensor. Then something happens. I don't know, maybe some electrostatic discharge might damage the sensor, or you suddenly have some interference. You may have some vibrations in your system, like mechanical vibrations, and this typically will manifest itself in a different shape of this Gaussian distribution. So it will still be a Gaussian distribution. It may still have the same mean value, but the variance will be much wider. So what we are basically doing here is that we are looking at this shape, and we are checking if this shape looks like the one we are expecting. So let's take a look now on a demo in MATLAB. The demo that I have created is in Moodle, so you can run it on your own. And this time I have removed the requirement for the Arduino. I have kept it on Moodle. So if you have an Arduino, can still read through the serial line, or if you have an STM board, you can read from the serial line the data from some sensor, and then you can plot it in a histogram. But now I've just replaced that with a simulation in MATLAB. And what I will be doing is that I will generate some random samples. So my samples will simulate the acceleration that we have just seen in the chart. So I will generate acceleration of 1 plus some noise, and the noise is here, and we'll later play with the noise. And I will plot all this in a histogram. So in a histogram, that's a chart like this, and this histogram tells me how many times did I have some number that falls within some specific group. So for example, here you can see that for this number it was there 20 times. This number in the middle was there something like 28 times. And if you have enough samples, then this will be a normal distribution. So it will be a bell-shaped curve, like Gaussian distribution. So let's try it out. Here I have 100 samples, and I have chosen that I will split the histogram into 50 bins, and the bin is the category, like a box where it should fall. I have added here a half second pause, because I want that this resembles the sampling from the Arduino. So when I run it, we will see that how the individual samples arrive. I just need to close my previous picture. So once again, stop. I will just clear everything. I just need to clean my previous attempt that I've made before the lecture. So now we can see it in real time. We can see that the samples are added. So here, this would be like if you get the data from a real system every half a second, and you can see that fine. Here now I'm adding some numbers, and if we wait long enough, and if we have a higher number of samples, then this will start to look like the Gaussian shape, the Gaussian probability distribution. Now for my example, where I have only 100 samples, it will probably not look like exactly like the Gaussian distribution, but you can kind of see that it may look like that it will be very soon a bell-shaped curve. So you are basically plotting a shape like this, and then what you can do is that you can calculate the variance of your data. So you will find out that the variance, for example, we can do this here. Let's calculate the variance of this data. Let's call AZ vector, and let's see how much that is. So we can see that the variance in my example is 0.0018, which is that was expected, because here that's the number that I have entered in my production of a random noise. So the variance at the end in my case should be something like this. And you can do this in real time. You can calculate the variance. You don't need to plot really the histogram. This is like a graphical tool, but you can calculate the variance. What is my variance of my signal? And then let's say then there's something wrong with your sensor, and it will cause let's say much higher noise in your signal. So now I will produce a noise which has 100 times larger amplitude, and we will see the effect on the histogram, and we'll see that it will have an effect on the variance. So let's just erase everything. Let's run it again. Now on the histogram, we can already see that we have significantly different numbers than previously, because previously we were somewhere near 1 and the variance was very small, so we had a very narrow bell-shaped curve. And now we have a really huge variance, and we can see that the samples vary all over the place. So we measure the mean value of 1, but sometimes we get sample that it's even below 0, and sometimes we get sample that is around 2. So you can see that now the variance has changed significantly. And we will see that also if we calculate the variance. So now we should get some value that's around 0.2, and that's exactly the value that I have entered here in my noise. So simply by calculating the variance and by watching if the variance is under some given threshold, I can check if there is something wrong with my data. For example, if there is some interference in my data that comes in from somewhere. Let's now try to remove this pause, and let's now try to use some higher number of samples. So let's say instead of 100, let's say I am going to use, let's say 10,000 for example. So something like that. And I'll just run it again. Now it will be very fast because I'm basically without any pause. I will just plot the outcome, and when it's finished we'll see the histogram. And since now we will have a large number of samples, it should be much closer to the Gaussian curve than previously, because that's basically related to the number of samples that you can actually have in your data. So you can run this algorithm in real time. You can simply get the data from some sensor. You don't need to plot the histogram, although it's sometimes quite useful to plot it, for example, on screen of some measurement instrument. And you can, at the end, you can just calculate the variance. And if your variance has changed suddenly from some previous value, that you know that the process works within those boundaries, then you may raise an alarm and say, attention, something has changed in the process, and there might be something wrong. And this problem might not be only the problem with the sensor. It might be completely unrelated. So for example, you may have a problem with interference that is coming from some motor, and at some times when the motor is running, you may have this interference which will add you the noise in your measurements. This can happen typically in sensors that produce small electrical signals, such as thermocouples, for example, or strain gauges, because here we're talking about the voltage that's somewhere in the order of microvolts. And here we have the result. I could have speeded up, because here if I would remove this eye, it would be super fast. But anyway, here you can see that now I have 10,000 samples, and now this starts to look like really a Gaussian curve. So I could also apply, for example, some shape recognition. I could train some neural network, whatever. I could use a very complicated algorithm on this data to find out if it's wrong. But what we are basically looking for is the width, the variance of my data. Okay, so the second and very similar method will be to calculate the uncertainty of the measurement. I refer you to other classes, for example physics, or we had a class measurement in engineering that was talking about how we can get this uncertainty. And here is why we are looking for this. Let's say I measure again some variable. It might be, for example, temperature. Here I have correct data, and I have a small uncertainty. So let's say I measure something, like here they measure 60 something. So let's say this would be, for example, temperature. And I get this temperature, so let's say my mean value is 60, and my uncertainty is somewhere like plus minus 5. So for this particular process, it's fine. I have 60 plus minus some small uncertainty. And this uncertainty is small, so I will say that this is a correct measurement. And then suddenly something happens, either with the sensor or with the data transfer, and your uncertainty will increase like that. So you still have the same number, you still have roughly 60 units of your variable, but then you have a really huge uncertainty. Now if you would plot this into a diagram where you have time versus your variable, so for example x, now how will this look like? You have, let's say I'm looking for some constant. This is the measured value that I have here, this value, the 60 for example. And we never have this perfect reading, we will have some noise like that. The noise is around this constant value, and from the data I can calculate uncertainty. And then suddenly when there is some problem, for example again interference, then I will have a much different data. I will have data that looks like this. So in total the mean value will still be the constant value like this. I will still get my 60, but I will see a much different uncertainty. And if I do the online calculation of my uncertainty based on some known equations, I can find out that there is a problem with the sensor or with the data transfer. So in a chart it looks like this. You have some measured value and some interval where with a reasonable probability you expect that the data is correct. And you can see that we're basically again looking for the width of some interval. So what we will do is to set some threshold. We'll say if uncertainty is, for example, in this interval like that, then it's okay. But now we are outside of this interval, and then from this time on we will use a logic signal and we'll say that this is an error and that we should do something. So this method is not able to correct the problem, but it's at least able to tell you that there's something wrong with the signal. So let's say again, let's see again some demo in MATLAB that you can try on your own. It's in Moodle, and I will again use MATLAB to simulate the signal, and we will play a little bit with our data. So what this code is doing? It's that I will produce 100 samples. I need to specify what is a so-called coverage factor, and this is based on the document that's called Guide to Uncertainty of Measurements. In short, it's called GUM, and it is also based on the expected probability distribution of my system. So I am assuming that I have a normal distribution and that I want to have confidence in my calculation to be around 95%. For this case, you find in this guide to uncertainty of measurement that something that's called a coverage factor should have this value. Then what you are doing, well, I will plot the histogram as well so that we see what happens in the histogram, because in the histogram we will see it as well if there is some change. And then I have added an error for all samples above 60. So we will see that the first 60 samples will have a small uncertainty, small noise. So here I have used 0.02. This is the variance of my signal. And then for all samples above 60, I have increased the noise, the variance of my noise 10 times. So what I've done is that I have added a larger noise to my signal. And we'll plot this into the histogram, and we'll see what will happen. And I'm also calculating online the uncertainty. So here in this MATLAB window, we will see the uncertainty of my signal. And when I will be below 60, I will see a small uncertainty. And then above 60, I will see a larger uncertainty. So we'll see that by calculating online the uncertainty, I'm able to find out that there might be something wrong with my signal. So let's try it. There is again a half-second pause between each sample, so we'll see how this will add the samples. So let's run it. Now what's some problem in my code? Okay, I forgot some vector in my code, so it's quite strange. Line 20. Okay, I should not plot the histogram in advance because I don't have the AZ vector. So let's just generate the AZ vector as zeros with the length of n samples, so that this is just preparing the histogram for plot. So I will have basically one figure with two subfigures. One will be the histogram, and the other one will be the plot of my data that I plot directly. And I plot here the uncertainty, and I plot here the histogram. So let's just see if this is fine. So AZ vector 100 by 100. Okay, that's not fine, so I just need to add a 1 here. Okay, this should be, I think, okay. So now what we are doing is that I'm adding sample by sample the values. Here we can see the histogram that is changing. Right now, since I have added the zeros, then those are the zeros in my field that are slowly decreasing. And this is getting larger and larger. And it should be a Gaussian curve very soon. And this is my uncertainty of the data. I'm calculating the uncertainty based on all the previous results. And now I'm above 60. So at 60, what happened is that I have changed my signal. I have changed the type of noise. So before 60 here, we see that we had some uncertainty, and we were around here with the Gaussian distribution. But above 60, I have added a noise that is 10 times larger. And we can see now what has happened with the uncertainty. The uncertainty started to change, and we can see that now we have different value. So by setting, for example, a threshold, what should be my uncertainty, you can detect that there might be something wrong with the signal. I'm saying might because all this is based on statistics, and when we are calculating the uncertainty, we are playing with some probability distribution. So it's not 100% sure, but always you are selecting some confidence level. And you are also selecting this confidence level based on the number of samples. So if you don't know how to calculate uncertainty of measurements, then take a look in this guide to uncertainty of measurement document and see how this is done. It's not very complicated. The equation is basically here. You are calculating the standard deviation and then you're dividing it by the number of samples, and all this is multiplied by the selected coverage factor. So it's basically a sum that's quite simple. So by looking on this method, we can use this to calculate the uncertainty, and we can get an estimate not only of how much the uncertainty is, but also how is it developing in time. And in a process that's running without an error, you would estimate that the uncertainty is roughly the same for all the values for all times. But when something is wrong with your sensor, then the uncertainty will change. So this is threshold detection. You're detecting if this goes outside of some interval. Now the third method that I would like to show, but only describe it in words and not mathematically, is called SIVA. This stands for sensor validation, and it originates from about 1993 at the Oxford University. You can take a look on some papers that describe this method. One of them is referenced here. But I would like to show this method only because it allows us to give, let's say, more detailed estimate of what is happening in our system. Now this method, in this version where it was published in '93, this method is producing 4 states. So on the input of our data here, of our block, we have the raw data that's coming in from the sensor. On the output, we have the validated measured value. So this is the correct reading. We calculate also the uncertainty of our reading. So we're basically combining what we've seen here. We're validating that the sensor is fine with the calculation of uncertainty, and we give out both. So we give the measured value, the validated one, plus the uncertainty. And then we have some status output. And this status output is giving us info, what is the current state of this. The state might be clear. This is when no error is detected, and when your validated measured value is really based on last measurement. The other state might be blurred. This is a state, it's like a temporary state, that is saying us that we have detected some problem, and we have corrected that, and we have recalculated somehow the validated measured value, and we have increased the uncertainty. So this is still a valid state that we may use for control. And the third state is called blind. And in this state we have detected an error. We were not able to correct it So this output of our block here, this is based on historic data. So for example, we have detected that some samples are missing, and we took the last known correct value. So this is historic data. It's not the correct measurement. It's not the actual value that we have. And since this is not the value that's based on measurement, it should not be used for feedback control. Because in a feedback control, you get some data, you decide what to do, and then you control something. But with this historic data, you don't know what you should do. And then there is a last state that's called dazzled. And this state is a temporary state, and it tells us that there is certainly something wrong in the data, but we don't have enough info to detect an error. So in this stage, for example, we have one sample that is definitely wrong. So for example, it might be a peak. We measure temperature somewhere, and we say we know that the previous temperature was 600 centigrades, and now we measure 1000 centigrades suddenly in between two samples. So this is certainly an error, but we don't know what error this is. So this state dazzled, typically you go from clear to dazzled, and then you go to blind because you are receiving more data that is definitely incorrect. Let's take a look at an example. Now this example that's again in this paper about sensor validation. I see I forgot here to change the name, so let's change it. So in this example, they have used this method to find out errors in flow measurements. So they have used a Coriolis flow meter that measured a specific amount of liquid that was required for a batch of some product. And in this batch, they have tried to measure 100 kilograms of the material. And in the liquid, there were occasionally bubbles. So what this is doing to the Coriolis flow meter is that you will get a wrong reading, because the bubbles will have different properties, and they will not be measured correctly with the Coriolis flow meter. So the way they used that in the process is that they had a pump. Here they started pumping, so this is the flow rate. You can see it ramped up to some value. Then at some specific time they have stopped the pump, and this is how the flow rate had decreased again to some original value. And we are looking here for a total mass, so total weight. So they have used a second sensor, like a weight scale, and they've measured that it's 100 kilograms. This is an independent measurement. Then in both cases, here they have measured that it's about 100 kilograms. So you can see 100.05. Here they have 99.9 kilograms. So basically 100 kilograms. But if you measure the flow, you know that the mass that you measure is basically the area under this curve, because it's an integral of this curve. So if you have a flawless signal like that, then you can calculate the integral, and you will get the weight, because we know that the Coriolis flow meter measures mass flow. So if I integrate the measured flow in time, I will get the mass. Here we can see that without bubbles, everything is fine. The integral under this curve will give me 100 kilograms. That's the measured value of my weight, and we can see the uncertainty. It's like 0.1 kilograms. But what will happen if there will be bubbles in the liquid? So here are my bubbles. I think it's fine, no bubbles, but here we have some bubbles, and the flow meter will not be able to measure this correctly. We will have a lower flow rate that we are measuring. So although we receive in weight the same 100 kilograms, if we do the calculation just based on those data, so basically this area under the curve, we will get less weight. So here you can see 97.7.8. So by using the data from the Coriolis flow meter, we'll get lower weight than it's real, and we will get a higher uncertainty. And you can see here the uncertainty. They have calculated uncertainty as well in real time. So you can see in these regions where we don't have any trouble with the bubbles, the uncertainty is fairly low. It's fairly close to my measured value. But for example, here where we have the bubbles, you can see that this uncertainty, that's the darker blue interval, is much wider. So although by looking on the value I cannot tell that it's correct or wrong, by looking on the uncertainty I could tell that it's much larger than, for example, here. So this is the input data that they have fed into their algorithm. And they have also created this algorithm for critical applications. So let's say you would like to measure the speed of an airplane, or it will be like some critical process where you really need to be sure that this is a correct sensor output. So in this case, they have added a next state that is called secure. And in this state, you have the verified measured value derived from more sensors of the same variable. Both variables, if it's, for example, two sensors, both sensors are in this state clear, so you do not detect any trouble. And moreover, both measurements are consistent. I will be talking about that on the next lecture, what this actually means. So this is an algorithm that is working for critical applications. Now I will not go into details how this works. You can take a look on this paper. I just want to stress out that this algorithm exists. Basically what you are doing here is that on the inputs you have the measured values from several sensors. So you have a sensor for the same variable, here an example 3. For all three you get some info from this block that is telling you it's validated, there's no error, and it's based on the last measurements. So this is what's before the block. And here in this block you're basically doing some form of sensor fusion, and you're fusing those three numbers together, and on the output you have the value of your block, you have the uncertainty, and you have the status, which should be secure if at least two of them are in the clear state, and if all data are consistent. And here is an example that they have used in this paper. So they have measured temperature. Here we see that we have correct data. This is the temperature is always this line, this horizontal line, and the blue interval is the uncertainty. So they are calculating uncertainty, of course. Here we have a fairly small uncertainty, and we will say that this is the state where it's clear. So this is from one sensor. This is only one of them. So this is the first example. This is basically this algorithm. here. They are detecting if we are in the clear, blurred, or dazzled state. Then they have introduced some error at some specific time, and we can see that this uncertainty started to increase, and it first went to the dazzled state for a short period of time, and then it went to the blind state. So in the blind state, we know that we are operating on historical data, so we know that this is only our imagination, that it's there, and that the real measured value has, for example, changed like that with a step change. And during all this time, we can see that this sensor 3, is in the blind state. The other sensors are fine, they are all in the clear state. So we have 3 sensors in total. 2 of them are in the clear state, and the third one is blind from this specific time. Now, what will happen on the output of this combination block? We will check for consistency of the data, which we will do next week, and we will calculate some resulting signal. And this is how it looks like. This is again temperature. Now note that we have different scale here in temperature. So here they have the constant value. This is the estimated or validated value in this case, and this blue interval is the uncertainty. Here from time 0 to roughly 120 they had small uncertainty, so here this was in the state of secure and clear, because in this state, remember, we had all 3 sensors that were in the clear state. So all those sensors were working fine. And from this time on, we have introduced an error in sensor 3. And when you do the combination algorithm, you will see that we have 2 sensors that are clear, and the third one is blind. So we will not be in the secure state because our 3 sensors are not giving us the same data, but we still have a fairly large confidence that those 2 sensors work correctly. So we can be in the clear state, and we will simply discard the reading from the third sensor. So this is the effect on uncertainty. Uncertainty has increased somehow, but it's still not as bad as for the individual sensor, which we see would be over here. So we have combined the 2 numbers from the correct sensors, and the algorithm has recognized that the third sensor is bad, it's not valid, and it has discarded this third number from sensor 3. Okay, so next week we will discuss how to do this consistency checking, and we'll see also this as a graphical representation.